Yeah, actually, I didn't include any information about Kilimanjaro in the presentation. It's just about the work and the theory of a bit of what quantum annealing is and so on. But it's true that maybe a couple of words are good for context. Anyway, so Kilimanjaro is a company that does hardware, software, and theory for quantum annealing specifically, but also the theory part also does some other kinds of quantum computation. And yeah, we use superconducting flux qubits, and that's all I'm going to say about that as an introduction. Can I move this with this? I didn't try this, sorry. The answer is no. That's fine. Okay. Oh, no. I'm very sorry.
So did you plug this? No.
I did not. But also I don't know why I lost this right now. That is an excellent question. Yeah, no, this is. I mean, maybe the angle of the cable I changed slightly.
Este no va de todos modos, no se arreglado.
Ah, se ha movido. Bueno, antes.
No, pero tú no lo has tocado.
No, yo eso no lo he tocado. Está claro. O sea, si estaba, lo puedo mover a la otra mesa, si esto estaba funcionando aquí en vez de aquí, no sé. Igual.
¿Has probado a quitar el cable y luego ponerlo bien?
Sí. Sí. Lo pruebo otra vez si queréis, pero vaya. Lo raro es que esto esté así como que... Sí, no estoy reconociendo la pantalla.
Wow. Llave USB, PDF, lo metemos aquí dentro.
Venga.
¿Tienes animaciones?
No tengo PDF.
¿Alguien tiene una llave USB?
Aquí hay... Ah, no, esto no. Bueno.
Envíalo a mi correo.
Vale, dime.
Geslop.
Vale.
¿Tiene USB-C?
Sí, tengo USB-C. Mira. Ahí está en otro lado. Estamos ya en 50 alternativas. Espera.
Sí.
USB-C con el conector.
Con el cable.
Perfecto.
Bueno, la tengo aquí. Si hace falta, no tengo la boca de izquierda, la USB para meter la charla dentro del No, yo he dicho, la dejo aquí.
Total, ¿esto funciona o no funciona?
Esto tampoco.
No tocar, ya está. No pasa nada. Es que no tengo el pincho puesto. Pero es que no, solamente tengo una salida. Es igual, si lo muevo aquí, no te preocupes. No, pero lo muevo aquí, no.
Ok.
Vale. Ok. Second try. We're almost there. All right. So who knows a little bit about quantum annealing here? Okay. Who knows a lot about quantum annealing? Just in case. Maybe you should come here. Okay. So yeah, also I was very much emphasized that I should make an introduction to this topic, which I think is very, very much normal. Also, I'm used to do this because not that many people know much about quantum annealing actually. So don't worry, you'll get it. So quantum annealing appears in the title of this talk. That's also why I want to explain it very well, which is going to be about scalable to local architecture for quantum annealing of all-to-all Ising models. This is a project I did in the context of my thesis. And it's, as you will see, well, essentially a graph of a hardware like graph that you can build to try to embed this fully connected Ising models in something that will then be used to do annealing. So quantum annealing is an algorithm, okay? It was introduced slightly before the 2000s, so it's rather old already. And it essentially consists of interpolating between two Hamiltonians. In its like, is everything good? Well, when it was originally conceived, well, it can be done as a heuristic, but actually the nice thing is that if you consider this process to be adiabatic, then you can do some nice robust theory about it and look at complexity of things. But the main idea is we encode a problem in the ground state of a Hamiltonian, and this will be our problem Hamiltonian. And since we encoded a problem in this Hamiltonian, this means that the optimal solution, so the minimum energy solution, the minimum cost state is the ground state of this Hamiltonian. So we would now like to prepare this ground state and measure it, and then we obtain the solution to our problem. But since this is a non-trivial Hamiltonian, because otherwise it would be a very easy problem, in order to prepare this ground state efficiently, what we are going to do is prepare the ground state of another Hamiltonian that is very easy to prepare its ground state. Say, for example, the transverse field. This is like a very standard choice. And then we're going to slowly interpolate between the two. And this slowly is just slowly enough such that the adiabatic theorem is respected and you don't excite out to the higher energy levels. Okay, so this is the, since we have the existence of this adiabatic theorem, this is kind of a guarantee that this algorithm will be exact as long as the gap between the ground state and the first excited state doesn't close. If you allow yourself to go arbitrarily slow, then you will always be able to preserve your full probability of being in the ground state at the end. All right. By the way, I didn't say it, but if at any point you want to stop me and ask questions, this is also perfectly okay. Now, I explained this a little bit already. So when you do this algorithm adiabatically, then you are doing adiabatic quantum computing. And this is no longer now the algorithm. So this additional assumption of adiabaticity makes this a whole computational paradigm. And now here you can do like complexity theory stuff and prove theoretical things, which is not that easy to do on the previous framework alone, because then you have usually a bunch of diabatic things going on, and solving those dynamics is not that trivial. But yeah, the parameter that controls the efficiency of this adiabatic algorithm, mainly, if you want, is the minimal gap along the computation, because your adiabatic time will go inversely with this minimal gap. Well, will go inversely with the gap along the full computation, but obviously this will be your bottleneck. And this is essentially something that we care about a lot in this framework. Yes. Is everybody clear on what this landscape, what this graph is showing? Because this is kind of very intuitive, but okay, I can say it before. I can say it better. So these are just like the lowest energy levels of this Hamiltonian here as you vary, as you interpolate from the first Hamiltonian, the initial Hamiltonian, to the last one. And this would be how these energy levels change. Here is, well, just because of the specific choice that I'm plotting here. But here, this is the transverse field. So the first excited subspace is degenerate. And in this particular choice, which I don't remember which Hamiltonian I'm plotting in particular, but it turns out that this is also the case. But this doesn't necessarily need to be. This is quite common. This not so much, essentially. HF is the problem Hamiltonian, the one that encodes your... Ah, sorry. No, that's supposed to be an F, definitely. Right. Well, it will have to do with time evolution because yes. So, but you will in the end have your initial state be this, and then you will time evolve because you will normally not satisfy the adiabatic condition. And also, in theory, like ideally, you won't be able to diagonalize these Hamiltonians for very large system sizes, right? That's why you want to make it physical. Okay. The second part of this title refers to this fully connected Ising models, which you are all perfectly familiar with here, I'm pretty sure. But why do these kind of models relate specifically to quantum annealing? Well, this is because they are a framework that allows to encode many classical optimization problems through this kind of formulation that we have here, this quadratic unconstrained binary optimization problems. It's essentially if you have a problem that you can encode with binary variables, you can forget about the unconstrained part, you can add constraints later. And then you can write, and it's quadratic, then you can write a cost function that just looks like this. And this, as you can already see coming, will map very easily to the Ising model. And then with this very general kind of way of writing a cost function, you can actually describe many interesting classical optimization problems, nerve scheduling, like machine learning, also portfolio optimization, network problems, even as local if you would like. And yeah, as I was mentioning before, this then relates very fast to just an Ising model. No? So if we are able to implement this kind of Hamiltonian, then we might be able to build a machine that is able to run this kind of computation. Yeah, I said easy-ish to build because obviously it's quantum technologies, nothing is easy. But it is true that this kind of Hamiltonian is actually the easiest to engineer in many platforms already today. And this, yeah. Sorry? I see. Which one? No, these are, well, this is the operator. Yeah, sorry, this is like bad notation actually. So here I wanted to make this jump between these variables. So here it's numbers, but then you promote these two operators. Well, it's a quantum Hamiltonian that is diagonal, so it's describing a classical problem. Exactly. So so sigma is the sigma z operator. Then during the evolution, you will have also X terms here. So when you take the expectation value during the evolution, you will have continuous expectation values of sigma z. No, sorry. This is a set. Yes. It's a set. Just it's either 0 or 1. It's binary. Yeah. So it's binary. It's either 0 or 1. Then we're going to map this to variables sigma that are also. Yep. Sorry. Sorry. No, sigma is well, if you want to see it there as a binary variable, and then we promote it to an operator, to a quantum operator. So from here to here, you mean? Yes. I am going to talk about that for a bit right now, because this is a question that a lot of people have immediately, right? So yes. Yes. Two local just means that I will only have two body terms in my Hamiltonian. This is here, like, this is what we would usually think of when we are thinking about implementing stuff, engineering. But I put it, it's relevant because previous literature that does something similar to this does it with 4 local terms, which is harder to engineer. So this was like an improvement that we did. Okay, so I'm going to put an explicit example of how you would encode classical optimization problem in within this framework, so you can have an idea. It's actually quite simple. So, okay, we're going to look at the nurse scheduling problem. We have a number of nurses and a number of shifts that need to be covered. And we would like to assign these shifts to nurses. So we will have nurse I at like shift slot T. Yes. What? It should be.
Is green.
Yes, it is green. Maybe I can put it on a different way. Can you hear me if I speak closer? Maybe not.
Yes, we heard you much better.
Put it on my hair. I don't know if that's a good idea. Yeah. Okay. If I leave it like this, is it okay?
Okay.
I put it slightly closer, but then I can also just speak louder. If not, tell me again if you can't hear me. Okay. So we want to make this assignments. And then, so our number of qubits will kind of be quadratic now with these variables. So we want to assign these shifts to some nurses, and we want to impose some conditions in order to do this. So we would like to have X nurses per time step T. Okay, we can impose this kind of condition if we satisfy, like if we minimize the energy of this term. We would also like for nurses to be able to take a break. So we don't want to assign more than 2 consecutive shifts. Okay, then if we minimize this term here, we will be satisfying this condition. And then every nurse should have more or less equal number of shifts because we don't want to take favorites. So this kind of condition can also be implemented in a similar manner to the first, but like in columns instead of rows. And with this simple way of formulating our needs and what optimizes each of them, then we can simply add some Lagrange multipliers to each of these, so like a strong penalty that actually penalizes with a lot of energy the states that do not satisfy our constraints. And that's it. We have our cost function. And then now we do the promotion from these binary variables to the spin operators. Yeah, by the way, this just strong penalties that I mentioned are not just like that easy to put. You sometimes, well, you often need to optimize these for better performance and so on. It's not straightforward to pick them. Yes. So I mean, in general, because then you might have some other terms that, because in this case, all our cost terms are constraints, but this is not necessarily the case always, which means that, for example, if we were to have some further cost part that doesn't have this Lagrange multipliers, then maybe we do need like a minimal value of each of the strong penalties such that the solution subspace is actually pushed to the ground state. And also, you don't want to go too high on these because then the optimization landscape becomes a bit harsher. Exactly. There is not for the final Hamiltonian, but since the algorithm that we're going to use will go through quantum states, then they are qubits. But yes, in the end, you will read out bits. Yes, so it's the information that you want to extract in the end is n times n bits of information. Yes. So I actually did not put this slide. It may have been interesting. But the idea of quantum annealing is that you exploit, so regular annealing algorithm, what it does is it starts with a high temperature state and it reduces the temperature gradually such that you reach the minimum as you go to temperature zero. The idea of quantum annealing is to do an analogous thing, but instead of raising the temperature, you start raising the transverse field. And then instead of thermal fluctuations, you are taking advantage of quantum fluctuations. So the hope is that there are some barriers that you would have trouble tunneling through, well, that you would have trouble jumping if you were using thermal excitations that you can now tunnel through. The idea. Speaking about the fact of why we want to make these qubits. Okay. Is it okay up to here, more or less the scheme? Okay. So now we're going to move a bit closer to the graph part and the actual work. So where are we interested in scalable two-local architectures to do this? Well, I mean, the why is a bit obvious because we want to build large-scale devices that are able to do this. But why is this hard? Why can't we just like build this graph directly? Well, it's because it's not really practical to do this in engineering terms. In the specific case of superconducting qubits, for example, this is like a circuit scheme of a superconducting qubit, superconducting flux qubit. And here, what is your qubit is essentially encoded in this loop here. Here you have current flowing either in this direction or in this direction, and this dictates your 0 or 1 states. Now, the size of this loop determines also the amount of noise that enters inside your qubit. So you kind of want to keep this small. If you want to put a lot of things close to this loop, say to couple it to other qubits, which you essentially need to do by putting close other loops that then will couple to other qubits, you will need more surface area because you also don't want these guys to speak to each other. Same goes for feed lines that controls the flux that goes in here, which translates to the local fields and so on and so forth, and also the readout mechanism that you want to put. The thing is that there's a lot of stuff going on around here, and you want to minimize it. And the less couplings that you have around it, then the more you can minimize this area. Yes, I think that's all I wanted to say here. Hold on. So we don't want to do this straightforwardly. So what are the current solutions to do this? You maybe, who has heard here of D-Wave? Okay. So D-Wave is actually the oldest quantum computing company in the world. They started with this annealing stuff more than 20 years ago. And so they also hold the largest quantum devices available online. And they have, like, their most advanced systems have like 5,000 something qubits. The thing is that their qubits are not very coherent. But there they are. People use them to try a lot of optimization things. And actually, they claimed quantum advantage like maybe a year ago or so in simulating the diabatic transitions in an Ising model, which is what their machine is really hosting for very short timescales, which is where they are coherent. And the thing is that like 2 days ago, a paper came out that reproduced at least some of their graphs with tensor networks, but not all of them. So part of this quantum advantage claim still stands, at least. But it's actually the only one that hasn't been revoked yet. Then again, they were simulating their own Hamiltonian, and the actual applications for that particular simulation are up for debate. No? But that was a bit of context on D-Wave. So they have, the thing is that they have very large devices and they have had to deal with this, how to connect many qubits issue. And they have had to deal with this in a large scale for a long time. So what is the solution that they came up with? So they came up with specific graph families with as much connectivity as they could implement, essentially. And then for the connectivities that they don't have, they form strongly coupled ferromagnetic chains that then will ideally act as a single qubit, such that you can connect stuff that is further apart. This is like the standard solution, and importantly, this is also robust to fabrication imperfections, because if you're doing this large-scale chips, then maybe this guy doesn't work, or this coupler doesn't work, and so on and so forth. And well, the other thing is that since you have to find, since you have a particular graph, and then you want to embed another graph, you need to find what is the optimal embedding that you want to make, because you also have to skip over the stuff that doesn't work, for example. And you want to minimize the size of these chains, et cetera, et cetera. So there's an algorithm that calculates these embeddings for you, but it's actually very expensive. So there's an important, very important runtime overhead right now when running large-scale calculations like this. Another previous proposal. I'm not keeping track of the time, by the way. Okay. Is this thing that I talked about before that uses now 4 body couplers. And it's a nice idea. It looks very elegant when you write down the Hamiltonians and so on. And it's this proposal by Lechner, Hauke, and Solle. And what they do is they do a variable change and now consider only the parities between the original variables. So instead of now caring about variable 1 and variable 2, I'm only going to care about 1, 2, which now duplicates, well, quadratically increases the number of qubits that you need. But you can ensure by imposing some constraints, which will turn out to be for local, that this will then represent your original problem. And the nice thing is that these 4 body couplers just need to be very strong, but you don't care about the exact value that they have. And then you only control the energies of your problem with the local fields, which are easy to control. But the bad thing is that it's very hard to do these kind of terms, let alone do them very strong in the lab. And also you suffer from this, that if this guy doesn't work, then the whole size that you can tackle is reduced to this, which is a bit of a pity. Well, and there are also some other proposals that are more complex. It also doesn't scale that well, so we don't need to go into detail. It's also very late, so I'll just skip through it. That was a very, very long drum roll to what I actually did in my work. So we are going to jump into it right now. More questions about the introduction? I would say last chance, but it's not true. You can ask whenever you want. All right. So what is our proposal to achieve this all-to-all connectivity in Ising models? All right. We will start by targeting the representation of just a spin glass, no local fields involved. We will include it later. So let's think of the simplest example for flick. And let's see how we could try to represent this. So the first thing that we're going to do is partition our problem graph in terms of triangles. Exactly how this partition is going to be done, we'll be going over in a second. But the point is that we only need to ensure that we are covering all the edges and a couple of conditions more. So once we do this, each triangle, so each individual triangular cell, since we now have some set to symmetry, only requires 2 qubits to describe its energy uniquely. So now I put the arrows so that you see that these are spins, but actually what matters here is that the wiggly lines means that those spins are parallel, and the straight lines means that they are anti-parallel. And these are all the energetically distinct configurations that you have. So we can assign this to some configuration in our physical spins, the ones that we will put on our graph later. And we now have part of our encoding. Let's see how this then plays out. Yeah, so what I was mentioning before, in order to cover this full Ising Hamiltonian, we split it into this tiny Hamiltonians that will now describe these individual triangles. And in order to ensure that this is actually an equality, we just need to make sure that we go through every edge at least once, and that if we go through one edge more than once, that all the energies that we assign to those individual triangles associated to that edge sum up to the full thing. This makes sense so far? It's partitioning this sum in terms of these tiny cells. Yes? Okay. Okay. Perfect. So we have the requirements that we need on what our triangles should cover. We have then some physical, that each of these cells is going to be represented by a pair of physical spins. And within each cell, we will have this assignment. You don't need to go to the details just yet. But once we have these two conditions, then we can get this physical Hamiltonian that would represent the energy of the orange triangle for the two physical qubits that represent it. Now, so far, we have the representation of the cost function in terms of independent triangular cells. But once we read out the system, we want the triangle configurations to be consistent with each other. No? So then we have to impose some consistency conditions among triangles. So for this, it essentially means that whenever we have a shared edge, for example, between the orange triangle and the green triangle, I'm going to go distracting. The configuration that describes this guy and the configuration that describes this guy needs to be consistent along this edge. This is what we want to ensure next. So what happens from this slide to the next is just because within each triangle, we need to have an internal assignment of the configurations of the physical qubits. This is what you're seeing here. So we will always assign the all parallel configuration to the 0, 0 within every triangle. And then the rest are pretty much arbitrary. The only thing that we need to ensure is that the 1, 1 is always assigned to an edge that is not shared. But this we can always do with a particular algorithm. So if we do this, if we assign things like this, then we realize that these two configurations, which are associated to these physical configurations for the orange triangle, then have to coincide with these two configurations because of the edge they share. They have to coincide with these two, with either of these two configurations in the physical qubits that describe the green triangle. And the nice thing is that if you realize there's a ferromagnetic interaction that can give you this constraint very easily. And that's essentially how we are going to impose our consistency conditions. We're going to review all these shared edges and impose the corresponding two-local penalty that enforces that consistency. So once you do this, then the full graph for this four-body clique will look something like this. These are the pairs of physical qubits that represent each of the differently colored triangular cells here. And what's in thicker lines here are the JP penalty ferromagnetic interactions. Yes? So in 2 I cannot, because there's no way I can go through every edge with just 2. And not in 4 because it will be redundant, and I will essentially also run into the issue that I will have no other option but to run twice through an edge that I have labeled 1, 1. And then I won't be able to make this constraint too local. You mean if I have a larger fully connected? No, but I can, because like I cannot do this with these 4 qubits, that it doesn't run through the 1, 1. But if I add more qubits, then I can do it. So this is exactly what I'm going to do. That I will. Yes, exactly. So I will talk about the algorithm of how we're going to choose the triangles in a second. More questions? Yes. Here I'm only representing the energetically distinct configurations, yes. Because here, this 0, 0 is representing, because my original cost function was just a spin glass. Yes. Okay. All right. All right. So actually, maybe I should have left this slide when I was speaking before. But the idea is that we went from our logical problem, which looked like this, and this was whatever you want it to be, to a physical Hamiltonian, and that looks like the sum of the individual triangles, which would be like these tiny things, these tiny cells here, plus the constraints. All right. Now, how do we scale this up? So if we take this simple algorithm, which now looks a bit scary, but it's not, then we can ensure that the conditions that I explained before are met, that we go through every edge guaranteed, and that we are always able to leave the 1, 1 edge without repetition. Okay, so the algorithm is that for each, well, you first choose a reference node. For this construction here, it's going to be node 2. And then for each newly added qubit or variable, you make all the new triangles that need to be done to connect that qubit to the rest, always going through the selected node. With this algorithm, which, I mean, I didn't put like a sequence of slides to visualize it, but because I don't think it's that important, then you will end up with something like this. The other part, sorry, this is important. You then include the edge energies, or the edge energies, because we are now dealing with the spin glass problem, on the first triangle that they appear fully. Because remember that if we have 2 triangles that go through the same edge, then the energy assigned to that edge on one triangle or the other has to add up to the full thing. So we will just put the full thing on one of the triangles, the one that pops up first. If we do this, both in choosing the triangles and in adding the energies, we will end up with this graph here. Now, a lot to explain. Let's go to it. The triads of blue numbers that you see near each pair of qubits refer to the triangles that they are that these 2 physical qubits represent in the logical picture. So you see that for every triad, the qubit number 2 is involved. This is because this is our selected node. We're always passing our triangles through it. And then, well, if you do this in an orderly manner, then you see that you can actually, there's a structure to how the triads end up in this kind of triangular structure. And, well, this is just where the energies of the problem end up, sometimes in local fields, sometimes in couplings. But they're all within the cells that represent individual qubits. If you see like this represents a particular triangular cell, this another one, and they're always connected through these penalties, because these are our consistency conditions. Okay. Now, if you look a bit more closely, you realize that actually all this hustle ended up meaning that we created long chains of strongly ferromagnetically coupled qubits. Okay. This means that we can actually view this whole thing as making a change of variables and then expanding our variables in like in long chains of qubits. What are the new variables that we shifted to? Well, if you look, so I colored the chains in different colors. You will see that to each chain corresponds one local field alone. For example, this white chain corresponds to the energy between of the edge 0, 2. So then this chain is going to represent the parity between qubits 0 and 2. you see that this guy is then the energy of H12, and this chain is going to represent the parity between variables 1 and 2. And if you look at all of them, you realize that now the variables we're working with are the parities of the rest of the variables with respect to the selected node. Okay. So once we got this far, we can actually very easily include the local fields with what we have. Like, this is just a way to include it. It's not very important. The idea is that we do it like this because then we can recycle the variables that we already have. But now, if we add local fields, then we will now need 3 physical qubits to describe 3 logical variables. But if we do it in this manner, then we can still keep kind of this factorization that we made with the selected node. So this is all that's really important. I'm saying this because it's actually quite late. So if we add this 3rd qubit in this manner, then now we are able to split the energies of all these now 8 energetically distinct configurations with the 2 physical qubits that we had before, and now we add a 3rd one that we're going to call sign qubit. So we do everything exactly the same. In order to include this in this graph, we now included the additional sign qubits, and by following this rule of including the local fields in the first triangle that they appear, we realize that there are actually a bunch of sign qubits that are left completely disconnected from their own triangular cells. So we can just get rid of them. And then it turns out that we just added an additional chain, which, surprise, surprise, represents the orientation of the selected node. Now we have the orientation of the selected node and the parity of the rest of the nodes with respect to this selected node. We have the full information about our problem. Yeah, and this is what I explained before of what this change of variables has now done. So in the end, the nice thing is that we have ended up with a full graph that is of degree 3. So it's minimal, actually, to be able to host any kind of hard problem. So that's kind of nice for the noise and crosstalk reasons that I was explaining before. Now, your number of qubits is quadratic, which is essentially as bad as it was in the L8 set scheme as well. Well, it's kind of as bad as it's going to be. So that's not too terrible. And then, well, you have this number of couplers, which we as theorists don't really care much about. And that's it. Now, I put this first slide of conclusions, so I'm not going to tell you about this thing that I have in between parentheses, because I assumed that I would not have time to do this. So I'm very glad I used the last 2 minutes to do this. Okay, so we have presented an alternative way to scale up quantum annealing processors, which essentially amounts to efficiently braiding logical chains, long logical chains. It is maximally sparse, so it's optimizing definitely on this direction, at the cost of not being robust against faults in the fabrication, for example. Because then if it's the same case as what I explained with the prior art of the L8 set, if this guy is now dead, then my graph is effectively much smaller. But the nice thing is that all the couplings involved are now available in the lab. And actually, another nice thing is that for the case of superconducting flux qubits in particular, doing very strong ferromagnetic couplings is actually easier than doing, for example, strong antiferromagnetic couplings. So it's like easier to make this penalty strong enough, which is hard in general. Well, and then there's some things that I didn't have time to tell you about the fact that this very simple structure of the logical space now allows us to tackle some additional issues that always come with scalable architectures by means of proposing different, slightly different initial Hamiltonians that will respect the symmetries of the problem better, and then also give you like a better annealing process overall. But we're not going to talk about that unless you ask. So that's it. Do you have any questions?
Questions? Thank you, Anna. Questions or comments? Maybe we can go down again. For the initial motivation, if you use a different platforms in which, for instance, you can use external light beam to engineer decoupling between faraway links, would you still ion star, for instance, and then you use phonon modes or atoms you use it like, I mean, are there other platforms in which you would not have this kind of
So
limitations?
the thing is that is valid for gate-based. But the problem with annealing is that this coupling needs to be there always, kind of, as you are interpolating. Like, you would have to have these lasers be crossing each other and then potentially interfere if there's like another qubit on the way. So it's also not, well, I don't know, maybe you can actually put them all in this. So for trapped ions, I'm not sure actually. For neutral atoms, it's definitely about the distance. So you could not also just do all-to-all connectivity by putting a bunch of them together, because then you cannot control the intensity of the coupling. With trapped ions, it's about one that's less about, to be honest. I don't know if you can just-
And can you repeat the advantage of this design with respect to these other Hauch-Zoller?
Yes, so with respect to the L8Z, the advantage of the standard L8Z as it was proposed, it's 4-body couplers, so that is very hard to engineer.
Okay.
Then there are some modifications that allow you to make this too local, but then there's an overhead to pay in the sense that you have to introduce ancillas and connect more stuff. So now your graph is d equals 12, I think, or d equals 8. I'm pretty sure it was 12. But the thing is that even though it's still sparse with respect to the size of the problem, it's still actually quite dense. And also there are some features of the fact that logical subspace is fundamentally different from this logical subspace. This logical subspace has a simpler structure. But again, because these encodings are different, they will also produce better or worse results depending on the problem. If the problem adapts better to this structure or to this structure, it may work.
Okay. More comments or questions?
This is perhaps a general question. So in the quantum annealing, so how is the effect of the temperature came in? So you need close to 0 temperatures, right, to do that. And so how are the errors coming in with the not exactly 0 temperature?
So actually, the most important source of error of superconducting qubits, which is the platform I know the most about, as of today, is not so much temperature, because this acts on a longer timescale, and also you can prepare your device in such a way that actually your temperature is low enough so that this won't be a bother. But the main issue is more about the purity of the substrate. For example, you usually have like a lot of uncontrolled two-level systems that are just like wobbling around your device and then introducing flash noise with moving magnetic fields. But the temperature is not usually the greatest issue, but it's actually interesting because, for example, for the D-Wave devices, they made a lot of studies because the coherence times are not that long, as I said before. So you can actually observe the regime in which you stop being coherent. Well, because if you try to be coherent, you have to go very fast, so you will excite out of the ground state really easily. Then if you wait long enough, you have both thermalization bringing you back down to the ground state, and Yeah, so that's thermalization is bringing it back down to the ground state. If you wait long enough, it's just that you are not actually going to the ground state. You're just lowering it and maybe, but that's why. Very high up. But it's not usually energy.
Thank you. Thank you.
Have you fabricated this kind of architecture at Kilimanjaro? No?
No. Good. I mean, this would be like the simplest thing to do. Which could be done, but we haven't, also because like for small devices you might as well put more connectivity. And also like now the focus is in perfection in other things. Also this robustness to imperfections in the fabrication is actually a thing with current fabrication technologies. It's essentially like artisan work to do this thing at the moment. So it's very likely that there will be some mistake here.
I have one question regarding the scalability of this for the larger problem, because if I'm not getting wrong, basically the number of qubits that you have for this quadratic problem is of order n squared, no? Now you have n squared qubits, and now you are going to have a graph with n squared qubits, and you have to get all the triangles of this graph to represent in the physical system. And the number of triangles is going to be of the order of the number of nodes in the graph to the cube, no, or whatever. What's the number of triangle is very big. It's the combinatorial number of all choosing 3 nodes out of all the nodes of the graph. So it's okay.
With the algorithm that I just made.
But for instance, for this case, how many triangles do you need for 7 nodes?
So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
But those are the triangles involving node number 2. Is this all the triangles, or do you need? And how does it scale with n roughly? Is linear, quadratic?
It goes with the number. Oh,
I mean, just to have an idea of how, from the original problem, this scales to the physical final problem.
So it should go with n minus 2 times n minus 3. Because it's like a lower triangular matrix.
So sort of quadratic. So at the very end is order 4 with respect to the original. Okay.
So
Thanks. Sorry, right?
it scales like the number of qubits.
Yeah, but the number of qubits is already n squared. So now you have to scale deal with the number of qubits again. So it's order 4 with respect to the original variable. Okay. Just to know, I mean, I understand that you have to do the embedding and all that, but just to have the idea of the scaling. Okay, thank you.
Another thing that I forgot to mention before about the difficulties in implementing this, which is a difficulty in implementing well, a lot of scalable approaches, is the strength of the penalty couplings. Because this will also need to be stronger as your system size grows. So you need to be able to make this really very strong from the get-go to be able to sustainably account for the scalability, which is the issue we were also trying to tackle with the different drivers.
Okay. More questions or comments? No? No question from there. So let's thank Anna again.